All right, good afternoon, people from Calculus 2. So we are going to continue talking about surface areas of revolution and go with that, all right? So the first one I'd like to talk to you guys about, okay, and this is a fairly straightforward kind of a problem. Well, actually, it's a classic. Everybody who has gone through Calc 2 has gone through problem number 10, okay? So this is a very famous problem. It's called Gabriel's horn, and there's a reason why it's very famous. Okay, so we're going to have y is equal to 1 over x, and what we're going to do is we're going to do two things. We are going to check the volume of revolution, and we are also going to look at the surface area of revolution. Okay, so here we go. Okay, so we have y is equal to 1 over x. Okay, we want the volume of revolution. We're just around about the x-axis, by the way. So we're just going to do this. Okay, it's going to be x greater than or equal to 1. So we'll call that 1. So we're just going to revolve this thing around. Okay, so you can look at it, it's kind of like a horn-ish sort of a thing. Okay. So we're going to use cylinder method, right? So we're just going to take these pieces and rotate them around. So it's not, so we're going to go from 1 to infinity. And now we need pi r squared, right? That's 1 over x. That's my radius, 1 over radius squared, right? H, which is all of my little h's I've added up. Okay. So we're going to go ahead and we're going to write limit as a approaches infinity. Pi, we have 1 to a. Use your favorite letter. We have x to the negative 2 dx. All right. See, Kat that we did yesterday, she's got a lot to say today. All right. So this is equal to the limit. A approaches infinity. We have pi. Go ahead and do that. That's going to be negative 1 over x, right? Integrating x to the negative 2. We add 1. And we're going from 1 to a. I'm going to use the signs to change. Okay, so we're going to say that this is going to be, so evaluating, we're going to say this is going to be 1 over 1 pi minus limit, right, as a goes to infinity of 1 over a. So that's how that works. As a goes off to infinity, evaluating this limit, this is 0. So we just end up with pi, right? All our problems could be that easy, right? That would be a very nice thing. Okay, now what we're going to do is we're going to calculate the surface area. Okay, so it's the same shape, except instead of computing the volume, we're computing the surface area around it. So we're going to be picking out like these little ribbons, right? So remember that the surface area was B. We have 2 pi r, and then ds, the arc length. Okay, so the r is still going to be, right? Still going to be y, 1 over x. But remember that ds, right, is equal to the square root of 1 plus f prime of x squared dx. Okay, so my y being 1 over x, my y prime is negative 1 over x squared. Okay, so if I square that, that's going to be 1 over x to the 4th. Okay, so plugging this back in, right, so I have my surface area. That's equal to a to b. We have 2 pi. R again is just the x. It's the it's just going to be 1 over x. All right. And then we've got the square root of 1 plus 1 over x to the 4th dx. Okay. So let's rearrange this a little bit so we can do an x to the 4th over x to the 4th here. All right, we're going to call that x to the fourth over x to the fourth so we can add some fractions together. Okay. So here we've got limit, right, SA is equal to the limit as a approaches infinity of 1 to a. Well, I used to say this time. Okay, we've got a 2 pi. I've got a 1 over x. And then we've got the square root of x to the fourth plus 1 over x to the fourth dx. Okay, now I encourage you to go look this thing up on the YouTube on somebody else's channel because they're gonna have they're gonna do a better job than I just did. All right, they're all going to employ one little trick here that that they're going to deal with. Okay, is they're going to claim that x to the fourth plus 1 over x to the fourth is approximately equal to 1. Okay, it's a little bit bigger, right? It's going to be actually bigger than 1, right? So what we're going to do, because this is insane. Okay, this is a trigonometric integral with a trigonometric integral. I mean, we're probably going to end up with a secant to the fifth power in here and a secant to the third, and that's just a lot of trouble, especially since you're going to know the answer after you've done this problem. Okay, so what we're going to do is we're going to say that the surface area is equal to the limit a approaches infinity of 1 to a, and I'm going to claim that 2 pi 1 over x root x to the fourth plus 1 fourth is greater than the limit as a approaches infinity of 1 over a of 2 pi 1 over x. All right. So whatever this is going to be bigger than it. All right. And I think we can look at a Desmos. Like I didn't know I was going to do this at all, did I? So we're going from the green line, right? Y equals or x equals 1 rather, and then off to infinity. The red line is this piece, right? And the blue line is just the 1 over x, and you kind of look at it and say, wow, they get kind of close together real fast, don't they? Like, yeah, they kind of do. And then they're pretty much the same, or nearly the same, for the entire time. So we're going to be safe in saying that, okay? And like I said, almost everybody you see do this on the YouTube, they're going to do it pretty much the same way that I just did it. They're going to wave their hands at this and say, ooh, that's going to be too hard. And we're just going to say that it's bigger than that. Why would I say it's bigger than that? Why would that care? Well, I know something about the integral of 1 over x from 1 to infinity. You do too. So that's the surface area. That's going to be 2 pi. Limit as a goes to infinity. And 1 over x dx, right? That integral that's natural log of x, isn't it? From 1 to a. So this is going to be 2 pi times limit a goes to infinity of the natural log of a minus the natural log of 1. Well, I know the natural log of 1 is 0. What's limit is as a goes to infinity of the natural log? To an h of x is equal to natural log of x. And this thing just keeps getting bigger and bigger and bigger and bigger and bigger, right? Natural log of, e to the billion is a billion. Natural log of e to the trillion is a trillion. So this actually grows without bound. Okay, so this thing, this piece here, this diverges. Right, goes off to infinity. This diverges. And in this case, diverging really does mean what most people think it means. It's off to infinity. This is smaller than the integral I was trying to. And since this one diverges, what do you think this one's going to do? right? This one goes off to infinity. This is bigger. This goes off to infinity too. This diverges. So what we have here, y equals 1 over x. Right? Yeah, we're dealing with mathematical objects here, so please try not to come up with, don't let reality bump into your math. Okay? But this is a name. This is a very well-known problem. This is called the painter's paradox. Because you've got this horn, right? This Gabriel's horn, okay? That has a finite volume. It has a volume of pi, right? We did the volume of revolution. It's got a volume. The volume is pi. We could pour paint, right? We could pour paint in here. And we could fill it. We would fill it with pi units of paint. However, if we tried to paint the inside of it, we have to make it like an infinitely thin sort of a surface here, but you know, we're dealing with math, so there we go. Make an infinitely thin surface, we actually don't get to cover the surface area. So it can hold pi units of paint, but if I try to paint it, if I try to actually do the surface area, then I don't make it. I don't have enough paint. I'll never have enough paint. Okay. So that's kind of the paradox, because you think like, well, what if it was clear? I'm like, well, it would still hold pi units of paint, but you couldn't paint it? Like, no. Even if it was clear, it would look like it was. I'm like, it still wouldn't be. So yeah, it's paradox. It's kind of a neat thing to think about and ponder. And it's weird. Okay, that's all it is. It's really weird. And there are a couple of things that every once in a while you'll bump into something like this. Usually somebody else has found them first. That's why they have names. But yeah, you can fill it up with pi units of paint, but you can't paint it. You can't paint the outside. You can't paint the inside because the surface area is infinite, but the volume is finite. So weird stuff. Okay. But that's, you know, the fact that they hand you this problem and they say you go figure this out. Like, they didn't tell you were allowed to cheat, right? They didn't tell you were allowed to do this, but you're allowed to do this. You're allowed to make this approximation on this problem. Okay. I don't ever like to do problems like this on exams because like it truly comes out of nowhere. And if you're not expecting this, this is just one giant sucker punch. So this is not a good exam question, but it is a function, Gabriel's horn. It is a very well-known function, and this is a very well-known paradox. So everybody who's taking Calc 2 kind of gets to go through this. Okay, so you'll see it. Okay, so yeah, there's that. Why don't we go back to something that's more normal and think about something a little bit easier. Okay, so let's see here. Okay. All right. So yeah, why don't we think about this one? Okay. So what we got here, right, we've got x equals 1/3 y squared plus 2 to the 3/2, 2 less than or equal to y less than or equal to 4. Okay, so I don't really know what this graph is going to look like because I would have to like multiply by 3, take everything to the 2/3 power, subtract 2, and then y equals plus or minus this thing. Okay, so I just like to remember, right, that my surface area is equal to my integration, right, of the limits. We'll say C and D here. We have 2 pi r ds. But remember, we're going around the x-axis rather. So r is simply the distance from this curve or from the axis to that curve. This is y. So instead of trying to deal with a function, right, we're just going to call this y. So we're going to say my surface area is equal to CD. We have 2 pi. This is the radius, right, times its little surface area. And if you remember, like the arc length. The arc length didn't matter if it was dy by dx or dx by dy, right? So here's your chance to show that. So this is going to be 1 plus, instead of dy by dx by dy squared dy. And my limits are going to be in terms of y's. Right? So I tried to, yesterday I told you, like, I'm not going to try to do any funny business, and I'm still not trying to do a lot of funny business by doing a lot of approximations. But look how they handed you this problem. Which one was it? Right? They said x equals this horrible function of y. They gave us the limits in terms of y. They're screaming at you, do this in terms of y. Okay? So I'm not trying to trick you here. I'm going to give you the same kind of problems. But I really am. I'm going to lead you that little trail of breadcrumbs. I was like, oh, the limits are in y. The function looks like it would be really difficult to solve for y. I wonder if I should do this in terms of y. Like, you absolutely should be doing this in terms of y. I'm not going to stop you if you want to do it in terms of x. I will feel bad for you, but I won't stop you. Okay, I don't know if I can't vouch for the accuracy or how long this problem is going to take if you do it that way either. So when it's leading you, right, to do it in terms of y, I really recommend do it in terms of y. Okay, so they are screaming at you, do it this way. All right, so our surface area is going to be 2 to 4. I don't have to integrate over any singularities here. We have a 2 pi y, and it's just y. It's not like a function of y, it's just y. And then, well, we have x is equal to 1/3 y squared plus 2 to the 3/2. Let's go ahead and figure out what x prime is. Right? That's going to be 3/2 times 1/3 x squared plus 2 to the 1/2, right? The 3/2 came down in front, 1/2, and then we have chain rolls, so we have a 2y outside. Okay, so the 1/3s cancel, the 2's cancel. Oh boy, this came out of a textbook, right? Because all of this stuff canceled. We have a y times y squared plus 2 sitting here. Oh, to the 1/2. All right. So let's go ahead and put this in here. So we're going to have 1 plus parentheses y squared plus 2 to the 1/2 squared. Okay. Well, what do you suppose y squared plus 2 to the 1/2 squared is going to be? Well, that's going to be y squared plus 2. Then we're going to have, right, we're going to have a y here. Oh, y squared here, because this is 2, this is going to be a 2, and then we have a plus 1. All right, and this is still in a square root. There's a dy here, 2 pi y, integral from 2 to 4, SA. All right, so here we go. We have surface area is equal to, all right, we have 2 to 4. We've got a 2 pi y. And let's figure out what's happening here. We've got a 1 plus a y to the 4th plus e2y squared. All right. That kind of looks like I should be able to factor it, right? Let me just rearrange it and write it in descending form. That's y to the 4th plus 2y squared plus 1. If I didn't know any better, I would say that this would be y squared plus 1 squared. All right, and we have a square root around that. 2 pi y, 2 to 4 equals my surface area. So let's go ahead and take the square root of y squared plus 1 squared. So we have a y squared plus 1. We have a 2 pi y integral 2 to 4 times the surface area. We'll pull this outside in a minute. Now you have a choice, right? You could let your y equal, right? You can say let u equal y squared plus 1, 2y. Here's a 2, here's a y. So we can do it. Go ahead and do it that way. Okay, at this point, since I'm already halfway, I'm hip deep in it already, we might, or you could multiply this out and just integrate it directly. It's up to you. Okay, there's no one right way to do this. But since I've already gone through this, so I know that, pardon me, there's my du, here's my u. When y equals 2, right, because we're going from 2 to 4, then u is equal to 2 squared plus 1, which is 5. When y equals 4, then u is equal to 4 squared plus 1, which is equal to 17. Okay. So we're going to have surface area is equal to 5 to 17. Okay. I've got my 2y as my du. And then I've got u, du, and there's a extra pi here. Didn't account for that yet. All right. And then all we're going to do here is we're just going to say, well, this is pi, and then we have u squared over 2 from 5 to 17. Okay. And that's it. Just plug those things in and we're done. So pi over 2. What's 17 squared? What is that? 289 minus 25. 17 squared minus 5 squared. 264. 264 divided by 2. All right, so that's going to be 132 pi's. Okay, and now that's it. That's there we have it. Oh, there was a 1/3. No, the 1/3 I took care of it. We're good. We're all good. All right. So that's you know, a lot of these problems they are picked because something is going to happen here that's going to make your life a lot easier. Please look for that because it's not supposed to be like we've already tortured you with integrals that are almost impossible to do. Even on this one, we've still tortured you with the arc length, right? When we had the hawk drop the prey, we tortured you with integrals. Not all the integrals have to be insanely hard, okay? And generally, the further you go up, the easier they become, or there's like little things that happen that are going to allow you to make a little approximation here. Okay. So this one, oh, about the y-axis, fancy. Okay, so here we go. We got y is equal to 1/3, x to the 3/2. Okay, and we are going to go with 0 to x to what? 21. So just like we had, right? Just like we had for this one, this distance here, right? This distance here rather was y. If we're going to rotate around this axis, then we're going to have some kind of a curve, and this distance, right, is going to, my radius is going to be x. Okay, so my surface area here, right, is going to be 2 pi times the radius times ds. And the radius could just be x. So we have surface area is equal to 2 pi integral a to b x. And now I have to figure out what's this ds here. Okay, what's my arc length? And again, remember, it doesn't matter, right? If we want dy by dx squared or dx by dy squared. In this case, I'd like dy by dx, please. Okay, so what is y prime? Right? Y prime is 1/3 times 3/2 x to the 1/2. It's almost like the last problem we did, isn't it? Okay, so that cancels. So we end up with 1/2 x to the 1/2. Wow, I can't imagine. Boy, they were kind. Right. So we have the square root, right, of 1 plus 1 over 2 x to the 1/2 squared. All right. Dx. And we're going from x is equal to 0 to 21. Okay. So here's my surface area. That is equal to 2 pi, 0 to 21. Okay, we have x. Now we have to sort this out. All right, so this is 1 plus, it looks like x to the 1/2 squared. That's just going to be x, right? And half squared is going to be 4. All right, so let's put a 4 over 4 here. So we've got some arithmetic to do here. So we've got x root 4 plus x all over 4. I'm going to pull the, right, I'm going to say this is 0 to 21, x, 4 plus x, and then divided by the square root of 4, which is 2. Now cancel. Okay, so we've got pi integral to 21, x root 4 plus x. All right, you might remember doing a problem like this from Calc 1. I hope you do. You might remember doing this as an integration by parts. Integration by parts for this is ugly. So, I mean, I remember watching my business calculus students have to do it that way. And I really wish they would have remembered what we went over the first week of class, because let u equal 4 plus x, du is equal to dx. When you see this, right, you're like, I don't know, this is not going to work out. Well, x equals, right, x equals u minus 4. Okay, so what we're going to have here, I'm going to go ahead and change my limits. Okay, so we have u is equal to x plus 4. So when x equals 0, u is equal to 4. When x is equal to 21, u is equal to 25. Okay, so we've got a pi. We've got a 4 to 25. X is equal to u minus 4 in parentheses. 4 plus x is equal to u to the 1/2 du. Okay, like I said, you can do this by integration by parts. I never like to do that because it's ugly and messy, but and it's longer, a lot longer. So this is 4 to 25, u to the 3/2 minus 4 u to the 1/2. Okay. Before I came to CNN, I used to work at a place called Ball Aerospace. Ball, you might remember Ball. That's if your grandmother does canning, right? You probably have Ball jars in your house somewhere. And they make satellites now. Okay, you can see it's a natural progression from canning jars into satellites. But my job there was to shoot lasers at cameras to see what the damage was going to be. And we had a group there that would play the game of Go. I'm lousy. Okay. And the people that would teach me, they'd make a move and they'd lick their, I'd make a move and they would just put their hand, it would be a whole face palm thing in their hand. And like, what are you doing? And I was like, what? And they said, be more clever. Okay, that's 8/3. Okay, and it's 4 to the, oh, that's 4 to the, it's not 4. I should pay attention to what I'm doing. At least a little bit. This is u evaluated at 25 minus, and then we have 2/5 4. Okay, 4 to the 5 halves minus 8/3, 4 to the 3 halves. Okay, and we you know, we can play around with the calculator and get something out of that if we want to. Okay, but that's where we are. Okay, so we could even do something like this, right? We could say 2/5 25 to the 5 halves minus 2/5 4 to the 5 halves, factor out the 2/5, and then we'd have a positive, right? Negative times negative, so we'd have 8/3, 4 to the 3 halves minus 8/3, 5 to the 3 halves, and get that. Okay, so we could do something like that too, times pi. Okay, so yeah, I always think to myself, like when people do integration by parts like this, be more clever, because that's a little painful. This is much easier, but you guys remember that you've seen it before. Okay, let's see. 242. Okay. Tell you what, I think what I'm going to do is, because I know we did a couple of these before as well. Yep. I know we've done a couple of these before. I'm an exam question. I'm not giving you one you have to do substance rule on. Okay, no, I'm not doing that. If it is going to require a substance rule, it's going to be set up the integral, but do not solve kind of an affair. All right, we're not doing that. So I think I'm going to quit here. I'm going to cut it here. I think I got an announcement for this weekend. Yeah, but yeah, it's, this is not as hard as the chapter 6 stuff was. Okay, the problems are more complicated, so they generally hand you easier scenarios to deal with, which is good. And then we'll just go with that. Okay, so I wish you the best weekend, and I will see you on Monday.